In this video, we're going to be looking at geometry in 3 dimensions, and in this video, we'll talk about simple closed surfaces, the regular polyhedra, and cylinders and cones. Let's define what a simple closed surface is. A simple closed surface has exactly one interior with no holes and is hollow. And these are examples of simple closed surfaces. Each one of them has only one interior. There are no holes in it, and the interior is hollow. These two at the bottom are not simple closed surfaces. Now, this may be difficult to see from a two-dimensional standpoint, but here, this figure has a hole in it. So this will not qualify as a simple closed surface. This one has two interiors. By definition, a simple closed surface has exactly one interior. This one has two interiors, one in the top and one on the bottom. Okay, let's identify what a sphere is. A sphere is like a ball. It's a set of all points at a given distance from a given point, which is called the center. So usually a circle in 2 dimensions, if you put it in a 3-dimensional situation, it would be a sphere. A solid is a set of all points on a simple closed surface together with all interior points. Okay, now some of these are solids. Like these two right here. Those are solids right here, these first two. And a polyhedron is a simple closed surface made up of polygonal regions or faces. The vertices of the polygonal regions are the vertices of the polyhedron, and the sides of the polygonal regions are called edges of the polyhedron. So in this case here, these are examples of polyhedra, which is the plural for polyhedron. Okay, because you have edges, and you do have vertices, and you do have faces that make up that polyhedron. And what are not polyhedron are these. Of course, there are no edges here in a sphere, and the same holds true with this one right here, because it doesn't have pretty much polygonal faces. This one, of course, has a hole in it, and this one has two interiors, one on top and one on the bottom, because those do not qualify as simple closed surfaces. Okay, we'll talk about what a prism is. A prism is a polyhedron in which two congruent faces, which are called the bases, lie in parallel planes, and the other faces, which are the lateral faces, are bounded by parallelograms. So in this case here, the bases are shaded in blue. Those are the top and the bottom. Then you have 3 lateral faces. Okay, now again, this may be difficult to see from a 2-dimensional view. But in this case here, you do have 3 lateral faces. And you also have vertices. And then you have edges of that prism. Like line segment AD is an edge. Also, line segment AB is another edge of that particular prism. And we do have a right prism and an oblique prism. A right prism is defined as lateral faces that are perpendicular to the bases. So in this case here, these 3 are right prisms because they're perpendicular to the bases based on those red squares that you see there. Okay, so these are the lateral faces. Well, the lateral faces are in the front. These are the bases here, and those bases are perpendicular to the lateral faces in these 3. Now, an oblique prism is where those lateral faces are not going to be perpendicular. In other words, it may be leaning on one side. The prism may be leaning either to the left or to the right. So here, when it's leaning like this here, That's a oblique prism. Okay, next is the pyramid. What a pyramid is nothing but a polyhedron determined by a polygon and a point not in the plane of that polygon. Okay, so here, the pyramid, here's the base right here. In this case, that's the triangle. And we have a point that's not in the plane. That point has a special name. It's called the apex. It's usually the tip that's on the pyramid. So here, connect that apex to each one of those vertices of that base. You would have the pyramid. And in this pyramid, you do have your lateral faces as well. And the number of lateral faces will be dependent upon the number of sides the base has. The base has 3 sides, so that means that there are 3 lateral faces in this illustration. And a right pyramid is defined as lateral faces being congruent isosceles triangle. So in the right pyramid, you have your lateral faces that are congruent isosceles triangles. In this case here, we have a triangular pyramid, and then you have your square pyramid, and then you have your pentagonal pyramid. Each base is named, well, the pyramids are named by looking at the base. Okay, next is a truncated polyhedron. If one or more corners of a polyhedron is removed by an intersecting plane or planes, the polyhedron is a truncated polygon. So if a piece of this pyramid, in this example, is cut off, the top of that pyramid is cut off, then that means you have a couple of parallel bases. And this is what we call a truncated square pyramid. And also a truncated cube, where the edge of this cube has been cut off, so that edge is in the form of a triangle. And then part of a prism has been chopped off completely at an angle. So this is a truncated prism. All right, next is a convex polyhedron. A convex polyhedron is a polyhedron in which a segment containing any 2 points in the interior of the polyhedron is in the interior of that polyhedron. So in this case here, if I have 2 points inside this polyhedron, then that means I can draw a line segment that connects those 2 points, and that line segment is inside that polyhedron. Okay, that's what convex means. If you recall, I talked about a convex polygon, where if you have 2 points in that polygon, the line segment must be wholly contained inside that polygon for it to be convex. Then a regular polyhedron is this. It's a convex polyhedron whose faces are congruent regular polygons such that the number of edges that meet at each vertex is the same for all vertices of the polyhedron. And in this case, we're going to be looking at 5 different regular polyhedra, as you can see here. And it's sometimes called the 5 Platonic solids. One of them is a cube, because it consists of nothing but 6 squares. This one is a tetrahedron, because it consists of nothing but regular triangles, which are basically called equilateral triangles. And then you have regular triangles here, and this is called the octahedron. And the reason why it's called the octahedron because it has 8 faces, and the tetrahedron has 4 faces in this particular solid. The other 2 Platonic solids are your dodecahedron, because it has 12 faces, and they're all pentagons. And this one is an icosahedron, because you have 20 equilateral triangles put together. So there are 20 faces here. Okay. All right, the next thing I'm going to cover, and I'm going to skip these 2 slides here, is nets. And these patterns can be used to construct the 5 regular polyhedra. And what nets are, just basically you're just cutting out you're taking that 3-dimensional figure and you're going to cut it out in a way so that it ends up being the result of a 2-dimensional figure. So a cube cut out in the right places will end up looking like this. The tetrahedron in a 2-dimensional view would look like this. An octahedron would look like this. Because in this case here you have 8 equilateral triangles. The dodecahedron would look like this as a 2-dimensional figure. And then also the icosahedron would look like this as well from a 2-dimensional view. Okay, now let's look at Euler's formula. And we want to find out by looking at this particular table, what is the relationship between the number of vertices, faces, and edges of a polyhedron. And there is a relationship. Here, the V is your vertices, F is your faces, E is the edges of each one of these 5 Platonic solids. In a tetrahedron, there are 4 vertices, 4 faces, 6 edges. If we add 4 plus 4, you're going to get 8. Subtract 6 from 8, you're going to get 2. In a cube, you have 8 vertices, 6 faces, 12 edges. Add 8 plus 6, you're going to get 14. 12 from 14 will also give you 2. And in the octahedron, if you go to use this pattern of adding 6 and 8, you'll get 14. 14 minus this 12 will give you 2 as well. And the same for the dodecahedron. 20 plus 12 is 32. 32 minus 30 will give you 2. And the icosahedron will be 12 plus 20 is 32. Minus 30 will also give you 2 as well. So the pattern is this. Add the number of vertices plus the number of faces minus the number of edges. You're always going to end up getting 2. That's the relationship between the number of vertices, faces, edges of a polyhedron. Alright, let's look at cylinders and cones. In a cylinder, it is a simple closed surface that is not a polyhedron. It's formed as a segment, in this case AB, and it's going to be parallel to a given line, and that's line L, and it traces a planar curve other than a polygon. In other words, basically, a cylinder, you have to think of a cylinder as a circular Coke can, like a Coca-Cola can. So here, this is what a cylinder looks like. Because you have the bases, which are circles, and the face is around the circle, because this covers the entire circle right here. Those are your bases, and this is your lateral surface right there, as you can see. And here, this is an example of a right circular cylinder, and the other two, this one is an oblique circular cylinder. You can see that it's not standing straight up, it's leaning a bit to the left, and this one is just an oblique cylinder. It's not circular because the circle is usually a smooth figure. This one is not. Alright, next is cones. That's the union of the line segments connecting a point P with each point on a simple closed curve. The simple closed curve and the interior of the curve. Okay, so here's an example of what a circular cone looks like. The vertex is at the top, the base is at the bottom. Your altitude is, which is another word for the vertical height, is inside the cone. It starts from the vertex perpendicular to the base. And then you have your lateral surface, which is on the outside. Okay, you also have an oblique cone, which is where, that the cone is not standing up vertically. It's usually leaning to the left or to the right. And your oblique circular cone, the base is a circle, however, it's leaning to the left or to the right. Okay, so that's what cones look like. Okay, and that would conclude this particular video on geometry in 3 dimensions.